Hello and welcome to the fourth video in the series on programming with Python and R. So today we're going to talk about making your own functions. So here are the learning objectives. Of course, the first is that you want to know why you would even bother making your own functions, and so we're going to talk about the concept of abstraction and how that's helpful. You're going to learn the syntax for defining a new function, so what are all the different things that you need to type to make a function. We'll talk about the concept of variable scope, so how you'll have different variables within the function versus outside of the function. You'll be able to add your own custom error messages. Hopefully that will be a lot easier to understand than the error messages that you would otherwise get. And you'll be able to import functions from one file into another file. So really the overall goal here is that you won't have to copy and paste your code so much, and by avoiding that you're going to make a lot fewer mistakes in your code. So my grandfather was an outdoorsman who did lots of nature education and hiking and stuff, and he always said you don't get extra points for suffering. So if you are spending 3 hours copying and pasting big chunks of code and then carefully editing it, you might feel like you're working really hard and should be proud of yourself, but really you're putting yourself through a lot of work and probably a big headache for nothing, when you could write your code a little bit better and just have to type things once and have it a lot easier to edit. All right, so we're going to work on introducing that concept. Okay, so as with all of the videos, if you go to the description, you'll find a table of contents. You'll also find a link to the dataset and some code to import it, so if you weren't following along with the previous videos, you'll be able to jump right in. And I'm going to show you both Python and R. I'd like you to actively follow along with one of those, and the other one just sort of passively watch it and get a feel for it. I recommend that for all of the videos where I'm showing both of the languages, you can always go back and watch it again if you change your mind about which language you're more interested in. And just as a note, there's a good breakpoint about halfway through this video, and I'll point out when that is. Okay, so what is abstraction? It's actually something you've been doing already without really thinking about it too much. So anytime, say, we take a value or a set of values and assign that to a variable name, we're doing abstraction, because now, like that, that's data. That's really, ultimately, it's a bunch of ones and zeros in your computer, right? But you've given it this name, so you just need to refer to it by this name, and then that accesses your data. Right, so that puts things in simpler terms for you to think about. And so we do abstraction with how our code works as well, right? When you type a function name, that's representing a bunch of computations, but you don't really have to think about how those computations work. So we're taking a bunch of code and we're putting it into this magic black box that we've given a name. And we don't really need to think about how it works anymore. We just need to say, okay, I know that if I use this function name, it does this. And if it doesn't, if it's not working right, we can then open up that code and take a look at it and see what's going on. I mean, hopefully you don't have to do this too many times with existing functions that other people have written, although sometimes you might. But anyway, I mean, modern programming is just impossible without abstraction. I mean, you can think of any piece of software you're using nowadays as like an onion with layers and layers and layers of abstraction. I mean, even think about when you type a number, like if you type in 2 plus 2, right, that's really simple. You're like, well, that doesn't represent anything more complicated, but what is your computer doing with that information? You type in these characters, it's turning these characters into numbers. I mean, you've written it in decimal, it needs it in binary, it has to convert that, and then there's an operation on the processor that's adding those numbers together. But you don't have to think about any of that. Like, you just have to think about, I learned that it works this way in math, it's going to work this way on my computer, done. So you're going to learn how to make more layers of abstraction by creating your own functions, and so by having those layers within your own code, you're going to make it easier for you to understand what's going on and easier for other people to understand what's going on, and that will make it possible for you to write better code and more complex code. Okay, so as I was just saying, biggest reason for making your own functions is abstraction, and you're making that magic black box where you figured out how to do something once, you don't have to think about it anymore, you just have to remember the name of your function, and then it will do that complex computation that you created. And as I was saying, this is going to help you avoid copying and pasting your code. Like imagine you wrote a bunch of code and you needed to run it on a bunch of different data sets or different pieces of your data set, and so you've copied that code 50 times. And then a week later you take a look at it, maybe have a chat with your advisor, and you're like, oh, I did something wrong with that. Do you want to go back and remember every place you copied and pasted that and try to fix it in the same way? And do you trust yourself to not make a mistake when going and fixing it 50 times? If you put that in a function definition instead, you'd only be changing it in one place, right? And you can add your own error checking into the function. So if something is wrong with the input, you can make a nice little error message to tell you. And so in general, this is going to make your code easier to read because instead of a big long chunk of code, you have a name that describes what the code is doing, which is your function name. Okay, so whether we're working in Python or R, we're going to have sort of the same basic structure to how a function is defined. So we're going to have a statement at the beginning saying we're making a function. So a statement is just basically a keyword in a language that itself isn't really a function, but it indicates some component of a command. All right, so in Python, it's going to be this three-letter word def that says we're about to define a function. And in R, there's a statement called function that indicates you're going to make a function. So you'll also have the function name as part of that definition. You'll indicate what the function arguments are, and you may or may not give those default values. You're going to create the function body, which has all of the code that the function is going to run. And then at the end of the body, you're going to have what's called a return statement, which tells the computer which value it should return out of that function when everything's done. All right, so let's start out in Python, and we'll start with a pretty simple example. So I am going to grab this line from my previous script, which will take a bunch of variables from my import script. All right, so now by putting this line at the beginning of this new script, I have some data to work with. And I'll save that. Let's call it making functions.py. Okay, so let's say I wanted to convert my elevation from meters to feet. And one way we could do that is simple multiplication. So I could say I wanted the first elevation value I could do that. And because this is a NumPy array, I could convert the whole thing at once. Just for an example of how I might be wanting to do this multiple times. Right, I'll save that, and I'll run it. Oops, I meant to print out the second one. Right, so it's like, okay, there it printed the first thing, it printed all of them. So I've done that conversion. But let's say later it's like, oh, you know what? I don't think this is precise enough. I want to do it with more precision. Right, now I'm changing it in two places. Right, and maybe like I made a mistake in one of those places, right? Because if you have to change something multiple times, there's more of a chance that you have to, that you're going to make a mistake one of those places. So, I mean, one level of abstraction you could do, and honestly for something this simple, it would be fine to do it this way rather than making a function. So you could say make a variable feet per meter, and then I could type in this number that I want. All right, and now I've only typed this one place in my script. If I decide I change my mind about what that number is, I've only got one place to change it. And, well, let me fill it in here. Another sort of bonus benefit of this is that I no longer have to remember like what this number was for and what it was doing. I have this variable that's a description of it. Right, so now I can run that and it's going to do this conversion everywhere, and now I've fixed it everywhere by having this one place where it can get changed. Okay, so let's say I want to make that into a function. And again, this is a very simple example. This might be simpler than most functions you ultimately make, but I'm doing it for the sake of showing you like what are all the pieces that you need. Okay, so in Python, like I mentioned, I'm going to start with this keyword called def. Right, and then I want to define the name of the function. So let's call it meters to feet. Very descriptive, and we know exactly what it does then. And so I'm going to put parentheses then after it, right? Because it's going to be a function that I'm going to use this way with these parentheses in here. And inside the parentheses, I put the names of the arguments that I want, and separated by commas, a lot like if you were calling the function. But in this case, I only have one argument, right? I'm just going to have a distance in meters, and I want to convert that to feet. And so after that, I'm going to type a colon. And if I hit enter, now I notice that Python has, or Thonny has automatically indented that for me. So this indentation actually in Python has meaning. It means I want to group all of these commands that are underneath under this one command. So by indenting in Python, we're transitioning from the beginning of this function definition to what inside here is going to be our function body. So let's say our output equals our input, that input argument, times, and here I am going to copy and paste this. We'll talk a little bit more about what would happen if I use that variable up there. Right, and then I have my return statement that I mentioned, which is ending the function body. You'll notice after I hit enter, after I made that return statement, it got rid of the indentation on the next line, because as soon as there's a return statement, that tells the function that it's done. So this is what is going to get output by the function. And now that I have that defined, I can use it. Oh. Right, and I can even overwrite these variables. This might be a place where I would want to start commenting out. Yeah, we'll comment out my previous version, because I don't really need to run all of that twice. But by leaving it here, if I want it later, I still have it. All right, so now I have this function definition, and I have some commands that use the function, and then I'm going to print the output just to make sure it does what I think it does. Right, and now I get the exact same output that I got last time. Okay, so let's take a quick look at how to make the same function definition in R, and then we'll have a little break with an exercise where you make your own function in the language of your choice. So I'll make a new R script today. Here we'll be making functions.r instead of .py. All right, and again, I'm going to grab some code for importing my previous data set from this data import.r script that we did in a previous video. So I can run that code, and here I'm pressing Control Enter to run that. And so then I get my data set, and as a reminder, I use this $sign to get the elevation one. And I see before actually I converted elevation to feet, but I probably did it with arithmetic, so now I will show you how to do it with a function. All right, so we're going to name the function the same thing. We'll call it meters to feet, but we'll set up the syntax just a little bit differently. So in R, we're going to put the function name first, and then we're going to use the assignment operator, just like we were making a variable, right? And then we have the function keyword after that. And we actually put the parentheses after the function keyword, and then we put our arguments in there, right? So after that, we're going to want the function body. And in R, we make curly brackets. So I typed an opening curly bracket, and it automatically filled in a closing one for me. And so our function body is going to go inside those curly brackets. And that's how we're going to group those commands together. And RStudio automatically indents for me. I highly recommend using that indentation, but in R, the indentation doesn't actually, it doesn't matter for the computer. It should matter to you for making it readable though, right? So much like before, I can define a new variable out, and I can say out is the value times 3.28084. And here I'll also have a return statement. And in this case, I'm going to put parentheses after it. Again, it's a statement, not really a function, but you see that both of these statements still had parentheses, kind of like they were functions. I'm going to say return out. All right, and then I can say my data elevation, we'll call it elevation feet 2 since I had an elevation feet in there before, is meters to feet, my data elevation, and then when I'm done with that, I'm going to print this out just to make sure that it is what I expect it to be. Okay, so I will run this line. I hit Control Enter at the beginning of that, and it actually ran the whole thing because it could tell this was a whole group of commands. And now I actually see the function listed in my environment. Right, and then I can run that elevation feet too, and I can see what it looks like and check that it looks like what I'm expecting. Okay, that was a very quick demonstration of how to do this in R. If you skip the Python portion to go straight to the R portion, maybe go back and watch it, because I do explain concepts in a little bit more detail and take a little bit more time with them in the Python portion, and they all apply to R as well. So for an exercise, I would like you to make a function that converts temperature in Fahrenheit to temperature in Celsius. And then you can test out and see if it works. For example, if you have 32 degrees Fahrenheit, that should be 0 degrees Celsius. 212 degrees Fahrenheit should be 100 degrees Celsius. So see if you can make a function that does that. Okay, welcome back. So let's make that function first in Python. Right, and I'll just start a new script for this. because it won't really be part of what I'm doing with this data set. So, right, so first step in Python is DEF, and then a meaningful name. That's right. Okay. Pardon my spelling if I did get it wrong. Okay. And I don't have to call it val, let's call it temp for temperature. All right. And so step one is I'm going to subtract 32 so that 0 in Fahrenheit is 0 in Celsius. And because of order of operations, I'm going to put that in parentheses. And then I'm going to multiply it by a conversion factor. So for every 9 degrees in Fahrenheit, there are 5 degrees in Celsius. So I'll multiply that by 5 divided by 9, right? And I could call this temp 2, or maybe temp C. So slightly more meaningful. And then I will return that. Oops. I do not need parentheses in Python like I did in R. All right, and then we'll see if it works. So, okay, call this Fahrenheit to Celsius.pi to make it easy to remember what the script does. And I'll try that out, and look, perfect, it works. So it converted both of these temperatures correctly. Right, and so this is maybe a little bit better example of math that you would want to put into a function, because before it's like, oh, we have a conversion factor. Honestly, it's less typing to just put that conversion factor into a variable and then always multiply that by that. But in this case, we're performing multiple mathematical operations, so it's a little bit easier to have that in a function. If I wanted to do that in R, right? I would type my name of my function first, the function keyword, the name of an argument, curly braces, and then I would create a new variable here and do the math to do that conversion. So subtract 32 to get 0 equals 0. And then multiply by the conversion factor. For every 9 degrees Fahrenheit, we have 5 degrees Celsius. And then I want to return that output. And I can write a couple lines of code to test it. Right, and so I'll put my cursor here, run that line. Now I see I have that function. All right, 32 Fahrenheit is 0 Celsius. 212 Fahrenheit is 100 Celsius. Perfect. So now I'd like to take a few minutes to talk about variable scope. So this is going to have to do with if you define a variable name, where is that name valid? So for example, I used this argument temp like a normal variable inside my function body, right? And I created this other variable called temp C. But if I look over here in my list of variables, I don't see either of those. I just see the function definition. And maybe I'll try running my other script here. And I notice that my argument val and my variable out, they also don't appear in this list of variables. And we can see that in R as well. where I made this function that has temp and temp C in it, but I don't see those listed here, nor do I see val or out. I just see the function definitions. And I can test that to make sure they're really not there. Like if I type out val and try to print that out, it says it's not found. If I type out, that's also not found. So really, I don't have access to those. And that's also going to be true in Python. Right, if I try to run this script and then say print temp C, it says that's not defined. If I try to print out temp, it says it's not defined. So in both cases, I don't have access to those variables anymore outside of this function body. But the opposite is not really true. You may have noticed that I copied and pasted this number, even though I've just been telling you not to copy and paste. So I could put that variable in here. And if I do that, let's save that and run it, that works just fine. So the inside of the function body does have access to variables outside of it, even if they weren't part of the argument. Now the danger of this is that when you make a function, you want it to always behave the same way if it gets the same arguments. Like if you give it the same input, it should always give the same output. And by doing this, I'm giving a chance for myself to change this up here, and now I'm changing the function behavior. So that's not a great idea. I mean, the reason why there's access in the function body to things that all outside of the function body is you might make functions that call other functions that you've made, and that allows you to build those layers of abstraction. Now, if you really, for readability's sake, wanted to put that in there, I could define it inside here. Let's grab that number again. Right, and so now because there is one inside the function body, it's going to ignore what it got outside of the function body. Or if it's something that I think I'm really going to want to change it, I could make that as a default argument. And now I'm giving myself the ability to change that later. So in R, that access to variables works exactly the same way, and for exactly the same reasons you don't really want to do it that way. So I could put in feet per meter equals this number here. And then I could use that variable inside my function body. Right, so if I run that line and run this function, once again, I can run meters to feet and it will work. But if I change this number, now I'm changing the function behavior. So what would be better would be to put this down inside, or make it a default argument. Right, and that will work okay. And you'll notice I use the equal sign instead of the arrow. That's not, well, you need the equal sign if you're defining a default function argument like this, but for assignment, the equal sign can work instead of the arrow in R. It's just the arrow is usually preferred. So to review all that in PowerPoint form, you can think of, you have your function definition kind of nested within this global environment where you've defined a bunch of functions and variables. And inside your function body, you can access those variables and functions from the global environment, but the global environment can't access variables and arguments that you define within the function body. Right, and a big reason to do this is it prevents clutter in your environment. It means you don't have quite as many variables defined in your global environment, and that means you need to worry less about accidental overlap between variables. So that's handy. All right, and Again, if you use a variable in the function body and it's not found defined already in the function body, either Python or R is then going to look for it outside of the function body. And so the big reason for this is that you might want to make a function and then make another function that uses that first function. So that you can do. But we don't really want to create other variables that are accessed from within the function body, because that can cause the function to behave in unexpected ways. Okay, so as a mini exercise where I'm not going to show the answer, I want you to see what happens if you have the same variable name in your global environment and in your function body. So let's put this guy back down here, and like say you change one of these. Right, so which one is going to get used? So you can try this either in Python and R and just get a sense of how it will work. If you want to take a break, this is a good stopping point, and you can pick up at the bookmark a more complex example in the table of contents later. All right, so let's make a little bit more complex example, and then that'll give me a chance to show some more concepts. Okay, so I put this one back the way I like it, just so that it's working right. All right, so I have stem diameter and stem height, and if we assume that the stem is a cylinder, we can get stem volume. So let's write a function for that. And in this case, I'm going to need 2 arguments, right? So I can put them in like that. And right, so if maybe I want to get the radius, which is the diameter divided by 2. And then maybe I want to get cross-section area, which would be pi times the radius squared. I forget if I have quick access to pi in Python. Let me just type it out. I don't think I do. No. But let me define it here. And you know, if I wanted to update this later and make it more precise, I could do that. Right? And then volume would be the area times the height. And then we'll return the volume. But you'll notice that diameter, or I'll tell you that diameter was measured in millimeters and height was measured in meters. And let's say that we wanted both of them in cubic centimeters instead. So I could make an argument called diam multiplier and an argument called height multiplier. And then I could adjust them based on those. Right, and then so when I use that, let's put in those first values. I could say, okay, I need to actually divide that diameter by 10 to get it to centimeters. And I need to multiply that height by 100 to get it to centimeters. Right? And then so this is the output of that I get. But maybe I don't want to type that every time, and maybe I know that across my various research projects, I'm almost always going to be measuring the diameter in millimeters and the height in meters. So I could set these to have default values. Right, and then I would not need to type that in. But just like using any other function, if I want to change that, I can set the argument myself. So let's say that I did measure the stem volume in centimeters, and now I don't need to multiply that height by anything. Oh, except I need to put in the correct argument name. I saw that kind of as I was running it. Great, then it runs the same way both ways, right? So with the meters and with the centimeters, and letting it know that it's in centimeters this time. And I can do this virtually the same way in R in terms of setting those argument defaults. So let's make a stem volume function here. So we'll put in our diameter, we'll put in our height, and since I already sort of revealed the magic of making argument defaults, I'll just set it up that way here too. And because I'm running out of space, I'm going to put in a line break. That's totally fine. So you can have lots of arguments if you make a big complicated function. And I believe in R, pi is built in. Yeah, so I'll use the built-in pi. So I'll adjust diameter. I'll adjust height. Right, and then let's say radius is diameter over 2. Put in some spaces to make it more readable there. And then I'll say cross-section area is radius squared. This is why I accidentally did the caret before, is that this does work for squaring in R. And then times pi. And then we'll say volume equals cross area times height, and return the volume. So if I make that function definition, voila, it shows up there. I can test it out. Right, get that same result, and I can use my other arguments in the same way. If I say wanted to have my height in centimeters instead, I could do it that way. And as you might remember from the other video, I wouldn't have to name this if I did it, say, like, if I put all of them in, all of the arguments. But I think it's a little bit easier to understand what's going on if you name your arguments. Now I might be getting to the point where the set of arguments is getting a little confusing. Like I might look at this a year from now and wonder, like, what exactly are those multipliers? What did I mean by that? And so in Python, traditionally you document a function with something called a comment string. So immediately after this def line, I put a line break, and I'm going to just put in a string right there. And here I type 6 single quotes, and basically in between those I can type whatever I want for my string. The three quotes on either side, this is going to allow you to have line breaks in your string. All right, so let's say estimate volume of a stem, assuming a cylinder, and then maybe I want to have some more information like diam is diameter, height is height, default assumes diam is in millimeters, height is in meters, output is in centimeters cubed, right? And then use alt arguments to convert input units to output units. Right, and maybe you would want to write even more details than that, and maybe you would end up having a comment string that was longer than the actual code in the function, and there's nothing wrong with that. Just make sure you have an explanation that will tell you what the function is doing and how to use it. Right? And in R, there isn't something quite as formal as the comment string, but usually I add some comments right either before or after the function. So like function to estimate stem volume, assuming a cylinder, and then I might put in similar information there to explain what's going on. And if you're interested, there is a package called R Oxygen, which has a little bit more of a formal way to indicate what all the arguments are and what's returned and everything like that. But that's more if you want to build this into an R package. Okay, so here's an exercise I'd like you to try. And you might need to look back at the indexing video to help figure this out. So make a function that will take a list or an array in Python or a vector in R, and it will get the mean of all values above a certain value that you specify. And maybe experiment with having that value have a default value. And if that's easy and you want something a little bit more challenging, then try making an na.rm argument for whether or not you want to ignore missing data. And that challenge is going to be a lot more difficult in the Python version than in the R version. So if you're doing this in Python and you want to do that challenge, you may have to Google a few things. It may take you a little bit. And for a quick hint on how to get a mean of something, like say I wanted the mean of stem density, I could do in Python sum of stem density and divide it by the length of stem density. Right, so this is without the subsetting that I want you to do. This would be how you would get the mean. Or in R, we have a function called mean, and could put in stem density. And if we look up mean, then it has this na.rm argument. That we might set to true or to false. All right, and note that if you're doing this in Python, you can't use a period in the argument name. Use an underscore instead. Okay, welcome back. If some of that was challenging, don't worry too much about it. We're going to go run through it. It was supposed to be kind of a challenging exercise. So of course, let's get started making a function. Let's say def mean above x, we'll call this one. And let's say my list, I'll call something values, and then x is what I want it to be above. And if you go back and look at our indexing and slicing subsetting video, you'll see a way to do this. So I think the first step should be just get all the values that are above x, right? So v for v in values, so that's going to, I do need an equal sign here. So V for V in values is basically going to, one at a time, go through all of the values in whatever array or list we give to that argument. And then I can say if V is greater than X. And then I say the mean I want is sum of val2 divided by length of val2. Return mean. And maybe I want to document this. Right, and so I can test that it works. Let's put this in print. I don't know why I have this weird thing where I always type pring instead of print. You may have noticed that already. It's just what my fingers do. So we'll test this out. 3, 4, 10, 12. And then we'll say x. For x, we'll put in 9. And then for a more real example, we'll look at our stem density. We'll say we want values above 15. So if we run that, okay, this one gives us 11 because it's the mean just of these two. That's great. We don't know ahead of time what the answer should be for stem density, but 38.5 doesn't seem unreasonable. Could see what happens if we change it to something lower, then the mean should probably be lower, right? It's a little bit lower. Okay, so that works. And say we want to have a default for x, say x equals 10, we could put it in like that. And then we might want to fill in x like that, and we can experiment with, if we don't put anything for x, does it still work? Okay, so that works quite well. All right, and so ignoring missing values, again, this is way beyond what we've covered so far, so don't worry about it, but I'm going to show you how to do it. Because I was playing around with this, I already put this line in. So this was a NumPy array, and it has some NaNs in it. In fact, I can print it out to show you those, right? So that's where the missing data was. So I'm going to import that ability to make my own missing number, as well as a function to test if anything is missing or not. Right? And if I do is NaN on stem density, I get true where it was missing and false where it wasn't. And if I just press the up arrow to get that back, and if I put that again inside of any, it gives me true to show that there were some missing values in that. Okay, so then I might want to say, so let me make an argument here. Do I want to ignore missing data? So by default, I'll have that as true. So say if not NaRM, and again, this construction where I'm kind of looking at true and false and writing it out like a sentence, we'll get into that more in another video. So don't worry if that's kind of new and weird. Any is NaN values. So this is first going to check, did we say we're not going to remove missing values? And then second, going to check, do we have any missing values? And then I'm going to put a colon here, and it's going to indent again. So in here, I'm telling it whatever I want it to do if this ends up being true. Right, and then I'll say If that's true, mean equals NaN. So if I run that, by default it does what it did before, but if I change NaRm to equal false, and I have to put that inside of my own function call and not inside of the print command. It says it's not a valid argument for print, and it's like, oh yeah, I didn't mean to give that to print. I meant it to meant to give it to mean above x. So do that, and now it gives me NaN because I told it don't ignore missing data. Just give me NaN if there's any missing data. Okay, let's take a look at how we would do that in R. All right. So I'll set up a function like this, right? And maybe I want to have a comment saying what it does. Right, and so I'll have my arguments, my values, and my x, and then curly braces to put function body in here. So the first thing I do is want to find all values above x. And so in R I can do that by Boolean indexing. And then I want to get the mean of those values. And then I would like to return the mean. Okay, and I can make a quick test of that. And so here I'm going to construct a vector. So let's say 3, 4, 10, 12 again, and x equals 9. Right, so I'll run that function definition, I'll run my command, and it gets 11 as I expected. Let's see, and if we do that on our real data, in this case by default we're going to get NA, right, because by default this mean does not ignore missing data. Okay, so first off, say we wanted to have a default for x, we can do that. That's the easy part. So I can run that. Now that does everything above 9, or I could set it to something else. And then it's going to give me different results based on that. Okay, that looks good. So how can I control the missing data? So let's say I want my default to be true. So I can set that here. And then, okay, this probably, I bet this tripped you up too, because it probably just seemed too weird to work. Okay, so I said na.rm equals true. This na.rm points back to this one. And then this one is the function argument for mean. So basically I'm passing this down the line and naming it the same thing. I could name it something different if I wanted to. I'm naming it the same because then I immediately know what it means because I'm already familiar with that argument. So if I run that, I can confirm that my easy ones work. And then this one works too. And I can check that if I set it back to false, it will be false. Perfect. Okay, let's take a look at how we would put in error messages. And I'm going to be using an if statement again to do that. And so I'm going to modify this stem volume function to give me an error if the diameter or the height is 0. And for simplicity in Python, I'm going to assume that it's getting past one value, even though with NumPy arrays, maybe we could pass it multiple values. So I say if diam, let's say less than or equal to 0, because I don't really want a negative value either, right? So if I type less than and then an equal sign right after, that means less than or equal to. And to create an error in Python, I'm going to say raise exception. And in here I'm going to put a string describing what I want it to say. And then maybe I'll put in a similar one to height. Similar one for height. Right, because these are plants, I'm never going to have a 0 diameter or height, and that might mean that someone entered something wrong, or they put 0 for missing data or something like that. So I want to know about it. All right, and so I'm going to comment out these other ones for testing this other function here. And I will maybe, yeah, we'll take this and we'll try it out. We'll see, okay, what do I do if, what happens if I put in 0 for the height? Right, and then I got that error message. So that's handy because right now I am checking myself for mistakes, right? And I get a message that makes sense to me rather than getting some really weird result down the line that I can't explain. And the nice thing about functions is like all of that stuff where it's looking and checking for that, that's all wrapped up in the function definition. But when I use the function, that's all out of the way. I just know that it's automatically checking that for me. Okay, if I wanted to do the same thing in R, let's say if, and in R it could be vectorized, so it's a little bit easier. I'll say any diam is less than or equal to 0. And here I'm going to put curly brackets again, kind of like what I did when I made the function definition. So this will say, what is going to happen if that gets triggered. And in R, I'm going to make a function called stop, or this is probably technically a statement too, not a function. And then I put in the message. And I'll do the same for height. Right, so I can save that, run it, and then let's try this out. So here's what I normally get from stem volume. If I try it with 0, now it gives me that error. Right, now I got an error that makes sense to me, and that's really helpful. Lastly, I want to show you how you can put your function definitions in a separate file from your script. So let's call this one function defs.py. Right, and let's see. Because this will just have the function definitions, I don't need all of my data, but what I do want to grab is this NumPy stuff that I used in one function, my kind of advanced function. All right, and so what I'm going to do is anything that's a function definition I'll put in that file. And everything else I'm going to leave out, or leave in the script. right? And I could name this something other than function defs. It's just, right now it's kind of a hodgepodge of things, so I'm calling it something kind of generic. So all I've got in here is my function definitions and anything I needed to import for those to work. Now I can import from that file. So I can say from function defs import, let's say meters to feet. Let's see, we did stem volume. And we did mean above x, and those are the three functions that we had in there. And now, without having those function definitions in this file, I can still run the script. In fact, I'm going to uncomment a bunch of this stuff just to show that it all works. Right, so now I can run this, and it runs everything, including the exception that I left in right there. Actually, it stopped everything as soon as it hit that exception. So maybe I'll comment out this one, and then it can get to the end, right? So this saves me a little space, like I can do all the nitty-gritty, oh, how do I make this stuff work? I can do that in this one file, and then this other file can be like, okay, what's my analysis that's actually happening, right? So that just makes it a little bit easier to read if you have like a bunch of short chunks of things. Okay, so how would I do that in R? Let's make a new script, and we'll similarly call it function definitions. Function defs. And so I'll go through and similarly grab just my function definitions. And actually, because R is interactive, to make sure this works, to demonstrate it works, I'm going to completely clear out my environment before I run it. I'm cutting and pasting here. Right, and so how can this script call this other one? I may have mentioned before, it's the source function actually, and I'm already using source function here. So I'll just add in another source command. Yeah, actually I'll put it after this remove command since these two kind of go together. Right, so if I run that, here are the commands to get my data set, and then here's the command to get my functions. Right, and then I would be able to run these commands. And again, what this means is that my script is a little bit shorter and easier to read because I've put all of the function definitions somewhere else. And now I just have the analysis that I'm doing with some nice descriptive function names. So I'm like, okay, I know that this stem volume function is getting the stem volume. I don't need to look at the whole function definition to know that. But if something is weird, I can always go back and look at it. Okay, thanks for sticking that out. In the next video, we'll cover loops, which is another way to avoid copying and pasting your code.